Hello. We're constantly being reminded that Einstein said nothing can go faster than light. Here's a recent example from a free newspaper in which unruly neutrinos from CERN seem to be breaking the law. I feel sad about this because if it's true, it means that a spacecraft would take many years to get anywhere interesting. Consider, if we make a model in which the Sun is reduced to the size of a football on the centre spot of a football pitch, then the Earth becomes the size of a grain of rice in the penalty area, 35 yards away. Even at 186,000 miles a second, light from the Sun takes over 8 minutes to reach the Earth. In our model, this feels like a crawl. But the nearest star, Proxima Centauri, is 550 miles away in our model, and the Sun's light takes over 4 years to reach it. That's well outside the UK. So if our space rockets can't ever go faster than light, and probably only a fraction of the speed of light, we might as well give up ideas of expanding across the galaxy now. I find that thought a huge disappointment. Personally, I've never doubted the idea of absolute zero, that there's a temperature below which things can't get any colder because they're just completely solid and the molecules can't move. But I've always been suspicious about this idea that there's an upper speed limit, and in this video I want to examine whether it really is true or whether there's room for doubt. The first question is, did Einstein really say this? And the answer is yes, he did. It's towards the end of his paper on special relativity in the Annalen der Physik, the German periodical The Annals of Physics, dated 1905. Here it is in the original German. Roughly translated, it says, "So nothing can go faster than light, as we saw before." Not much doubt about that. We will return to Einstein shortly, but first of all we need to ask ourselves, what does the word relativity really mean? Consider this van. When we say we're travelling 50 miles an hour, we mean relative to the road. Relative to the cars in front, our speed is more like 0 miles an hour, and relative to the cars going the other way, we're separating from them at over 100 miles an hour. These are simple calculations. But suppose you wanted to work out the speed of this lorry relative to the Sun. You would need its speed relative to the road, the angle of the hill, the speed of the Earth turning, the latitude and longitude of the lorry in order to take the curvature of the Earth into account, the direction of the road, and even the time and date, since the distance between the Earth and the Sun varies slightly throughout the year. The calculation would be highly complex, but rather fun if you enjoy that sort of thing. Personally, I don't. I think I'll leave it up to you. When we talk about cars and planes, the frame of reference is obvious for determining speed. But once you come to spacecraft thousands of miles from Earth, it's a different story. I first learned this from the Voyager mission to the outer planets in the late 1980s. When Voyager 2 was approaching Neptune, they said on the radio that its speed was 50 miles a second. I like that. It was covering in 1 second what our van was covering in 1 hour on the road. At the time, I assumed that the 50 miles a second meant relative to the Earth. But that's wrong, because if you look at this reenactment, you can see that it must mean relative to the planets it's approaching, because its speed relative to Earth here is very different from its speed relative to Earth here. If we add in a distant planet and an asteroid and a comet, then the whole situation becomes much more confusing as to what its speed is relative to those, especially as in this instance the asteroid doesn't appear to know what she's doing. Never mind. We can be sure that Einstein was not thinking about permanently accelerating spacecraft when he wrote those words in 1905. At that time, the Wright brothers were only just getting airborne, and they were about to astonish the world with their fixed wing and propeller. There were only a handful of people in the world who considered that a space rocket might be possible. As humans, we're very slow to imagine what might be going to come in the future. Arthur C. Clarke, in this entertaining book, has some lovely examples of what he calls failures of vision and failures of imagination, and failures of nerve. My favourite is the one about the learned academic whose maths over several pages proved beyond doubt that no spacecraft would ever be able to get into orbit. The mistake he made was in failing to realise that the fuel would be burnt up as the craft went up, and therefore the whole thing would get lighter as it went. His calculations assumed that everything had to go into orbit the entire weight, so no wonder he was hopelessly wrong. So we'd better not be put off by entrenched belief in our search. We need to approach the matter carefully. If you're wondering how Voyager 2 came to be travelling so fast, it's because it used the process known as a slingshot, or gravity assist. By skimming over the surface of a planet, a spacecraft can gain momentum from the planet and speed up. It's rather clever. Voyager did this on 3 occasions at Jupiter, Saturn and Uranus. We're almost ready to return to Einstein's statement, but not quite. We need to point out that in any field, you have the experts up here, as it were, then you have the interpreters and commentators beneath them, turning the whole thing into something that you and I down here can understand. This is especially the case with this subject, because we read in this biography of Paul Dirac, the English genius in physics, the mathematical complexities of Einstein's general theory so terrified most physicists that they found excuses not to bother with it, whereas Dirac studied it voraciously. So in this particular instance, we're going to need a lot of help from the commentators, and they better be right. However, if you think that academics and writers are always correct, the answer is not always. Consider this example from the field of theology, once known as the Queen of the Sciences. When he was writing a commentary on the biblical book of Job in the 1980s, Professor Kleins came across accounts of the Indian Job, which was cited with some frequency in the recent scholarly literature. He determined to find the source of the stories. In his research, he discovered that the scholars had been quoting each other and not going back to the original source. He wrote up his findings in a paper entitled In Search of the Indian Job. His paragraph about the work of recent scholars in the field is a cautionary tale for scholars in every academic discipline and is worth reading in full. He writes that no scholar citing this story from 1836 to 1967 consulted the original, and the habitual form of reference cites the wrong author, the wrong title, and the wrong page number. How grim is that? This lack of thoroughness may apply in our field. After all, these authors are busy people, and with all the complexities, it must have been tempting not to go back to the original. Perhaps they could quote each other. Nobody would ever know. Or would they? With all these thoughts in mind, it's now time to return to Einstein's statement and the 2 papers of 1905 and 1916. Einstein's 1905 paper soon came to be referred to as special relativity, since it deals with a system without gravity and acceleration, which is a special case. It took him a full 10 years to incorporate gravity and acceleration into a general theory dealing with every case. In his 1916 paper, frames of reference have been abandoned, and we're presented with the concept of space-time, whose curvature explains the path of moving objects. Seems to me it's significant that the phrase "nothing can go faster than light" only occurs in the first paper, Special Relativity. I think a case needs to be made to say that you can transfer that understanding into the situation of general relativity. In other words, it only applies to a specialized world which is actually not the real world. Any idea of an upper speed limit for space rockets seems wrong to me, because as we saw earlier from our model, it's impossible to say what speed the rocket is travelling at. If you like, there is no frame of reference. Or if you prefer, there are infinite frames of reference, and the accelerating spacecraft doesn't need to violate any of them. You may think it impossible that a spacecraft could go on accelerating indefinitely, but I think that's to commit one of Clarke's failures of nerve or failures of imagination. I think that humanity is going to so master nuclear processes in line with Einstein's equation E equals mc squared that we use the entire power from nuclear reactions, and that therefore one day something as simple as a shovelful of Earth might provide sufficient energy for us to accelerate from here all the way to the centre of the galaxy. We're very slow to believe that technology is going to improve over coming years. If you doubt it, just consider how much has changed since the time of William Shakespeare. Try having an imagined conversation with Shakespeare in which you explain that you're fast forwarding through the adverts in the TV programme you're both watching. Even something as simple as the battery in a remote control would be incomprehensible to him. Shakespeare lived 400 years ago. From that I conclude that nobody alive now has the slightest idea of what life on Earth is going to be like in 400 years' time, and it may well be that constantly accelerating spacecraft will be commonplace by then. Now let's turn to look at one of the books which interprets Einstein's theories to us lesser mortals. This one, Relativity for the Layman, first appeared in 1953. It went through numerous reprintings, had a second edition in 1969, and was even being reprinted in 1990. So it's no exaggeration to say that it influenced a generation. Let's see what it says. Coleman makes the point admirably on page 47 that speed is always relative to something else. But the problems then start 10 pages later, page 57, where he says the mass of the fast-moving object becomes greater. He ought to say the mass of the object appears to become greater. And on page 60, he says nothing can travel faster than light because, as we have seen, not only does its length shrink to nothing, but its mass becomes infinite. He should say its length appears to shrink to nothing, and its mass appears to become infinite. I think he gets into a mess there. So while Einstein can write in 1905 that in a world without gravitation, without acceleration, nothing can go faster than light, in the real world it seems to be all you can say is nothing can be seen to go faster than light, and it would be helpful to express it like that. This will not prevent a spacecraft from accelerating indefinitely, in my view. Coleman states that at the speed of light, one's mass increases to infinity. But consider this. If I walk along the road, and we imagine the car driving towards me as a spaceship travelling a few centimetres per second less than the speed of light relative to the road, which Coleman says is a permitted speed, then according to Coleman, my mass becomes infinite and I shrink to zero size. This is clearly ridiculous. My mass only appears to become infinite and my size minuscule to people on board the fast-moving spaceship. As it stands, the phrase "nothing can go faster than light" is meaningless because there's nothing that it's related to. You have to say, nothing can be observed to go faster than light. I don't think that this is going to be a problem for accelerating spacecraft. I think they'll be able to accelerate indefinitely in practice. We shall see. Consider a spacecraft doing a gravity assist maneuver past a planet. I cannot believe that the presence of a galaxy moving close to the speed of light relative to the spacecraft in the opposite direction will put a brake on things just because the two will be separating at a speed faster than light can travel. But I am happy to agree that the separation may not be observable or measurable from that galaxy. Whether or not you agree with me, there is a practical consideration. Observing fast-moving objects is not straightforward. Here are some trains coming and going at a mile a second. They're not visible for long. Now let's speed them up to 2 miles a second. Please spare a thought for the poor passengers on board at the abrupt changes in motion. Oh, go on then. Here they are at 3 miles a second. Notice how quickly the trains vanish. You can imagine the difficulty of trying to observe things going at 186,000 miles a second. You remember Sherlock Holmes told Dr. Watson, "You see but you do not observe." Well, with these spaceships, it seems to me you observe but you do not see. This will be especially the case if, as I suspect, the spaceships are perhaps too small to be seen with the naked eye, carrying messages about. Don't imagine it won't happen. Personally, I believe that the day will come when sending a message by the speed of light will be considered rather slow, like second-class postage is today. If you're still not persuaded that there's a case to answer, then consider this. Some people hold that the universe is infinite. If so, then somewhere there'll be a galaxy that's moving away from me at just a centimetre or two slower than the speed of light. This means that by raising my hand to my head, I've suddenly reached a superluminary speed and broken this supposed law. In fact, you could say that every blink of my eyelid all the way through my life has been breaking this law. Well, that's a tough one to get hold of, and I don't believe it myself. To conclude, I think there's sufficient doubt about 186,000 miles an hour being an upper speed limit for us to keep an open mind on the matter. I hope one day we'll have rockets when we can try out these high speeds, because we won't really know until then. In the meantime, let's not get disheartened about expanding across the galaxy. just because of the mind-numbing distances involved and the difficulty of going fast enough. To conclude, here's the view from a spaceship taking off from our garden, accelerating promptly and using the moon for gravity assist to work up some serious speed on its way through some unexpected dark matter out towards the stars. Thank you for your attention.